just so that we don't have any distracting background noises. If you have questions, feel free to add them to the chat. I'll make sure to pause and address the questions at the end. You can also use the raise hand button on Zoom as well. So the first question, and all of these questions are available in the slides that I sent out earlier in the chat. They're also available on Canvas. But the first question is one involving two carts that are set up as shown. They're on two different hills, and they're attached by this pulley, or this string that goes over a pulley. And for this problem, there's no friction to deal with. So we have the carts released, and we want to figure out the tension in the rope and the acceleration of the carts. Okay, so before we do anything, when I look at this problem, the first thing I should really be thinking about is what are the relevant principles here? There's actually a couple different ways to approach a problem like this. We might be thinking that we could use conservation of energy. And as the carts are released from rest, the heavier one's going to go down, the lighter one's going to come up. So they're both going to have their energy change, their potential energy change. And if we were asked something about their speed, using conservation of energy would be a really appropriate and good way to go about solving this problem. Speed is related to kinetic energy. And if we can keep track of how their potential energy changes, we can relate that to kinetic energy and work out things like speed. But this problem actually asks about the tension in the rope and the acceleration of the carts. And conservation of energy doesn't tell us those things. It's not going to give us forces. It's not going to give us accelerations. But if we're looking at this problem, we see that we're trying to solve for a force and an acceleration. That should be a hint that we're thinking about Newton's laws. Okay, so if we're doing Newton's laws, then the first step is going to be to draw a free body diagram. And we have two carts, so we're going to have to draw two free body diagrams. And I'm just going to draw them right on top of the picture. So I'll call cart number 1 the cart on the left side. And I'm not going to plug in any numbers initially. I'm just going to call its weight M1G. And later on, I can plug in 10 kilograms for M1. And there's going to be some normal force. And there's going to be some tension in the rope that pulls this cart up the hill. Now, if there were friction, I would include that, but I'm told it's frictionless. So I am going to, in red here, draw the components of the weight that point down onto the plane and perpendicular. So this angle right here is the same 37-degree angle that I had for the hill. And so this downwards component of the weight is going to be M1G sine of 37 degrees. This component that's pointing in the what I'll call the minus y direction. So I'm going to choose a coordinate system where my x-axis is in the direction of motion. It's usually easiest if we align our coordinate system to the direction that something is moving or something is accelerating. In this case, both those things are going to be up the plane for this, this lower mass cart. So in the y direction, right, I've got M1G cosine 37 degrees pointing down and the normal force pointing up. So after you draw your free body diagram, you're going to want to say that the sum of the forces is mass times acceleration. That's almost always the next step in a problem involving Newton's laws. And the free body diagram is just a way to organize our forces. So the left side of Newton's second law, we're going to evaluate from the free body diagram. So I'm interested in the motion in the x direction. So let me consider the x component of the forces, and that's the direction of the acceleration. So I've defined to the right as being positive. So tension is a positive force, and the component of the weight that's pulling the block down is negative. So those are the only forces I have in x. Right? There's no friction in this problem, and if I'm just looking at cart 1, those are the two forces. So let me set them equal to mass times acceleration, and I'm going to make sure to use the mass of cart 1 because I've only looked at the forces at this point on cart 1. Okay, so this has the two things that I care about. It has tension, which I need to solve for, and it has acceleration that I need to solve for. But of course, I can't solve one equation for two unknowns. I'm going to need a second equation. And so I will switch over to orange here for the second object. And I'll do something very similar. I'll draw a free body diagram. And this time the tension is pointing up and to the left. Now, I'm going to want to choose a coordinate system again. And because it's a different object, I can change my coordinate system for this object. And I'm going to make x be along the direction of motion, just like I had for the first cart. So if I do that, then the components of the weight, there's a y component and there's an x component. I only really care about the x component, which is going to be m2g sine of 53 degrees, right? Because this angle is also 53 degrees. So now I can say the sum of the forces in x for this second block equals mass times acceleration. And by choosing my coordinates such that both blocks are expected to move in the positive x direction, then I can say the acceleration of the two blocks will both have the same magnitude. If one has a positive acceleration, the other one will also have a positive acceleration. So the acceleration of both in both equations that I write are going to be the same. Okay, so I've got m2g sine of 53 degrees pointing down, and I have tension pointing up. So they're in opposite directions. And the one that's in the direction of motion, this mg sine 53 degrees, that's in the direction of motion. So that's going to be my positive. And I'll set that equal to ma. Again, I'm using m2 here because I'm only considering block 2 in this equation. And now I've got two equations. The first equation had tension and acceleration, which I didn't know. And the second equation has tension and acceleration. So I have two equations and two unknowns. So I can solve for those things. So let me start with this first equation, and I'm going to bring this term onto the right to solve for tension. It's going to equal m1a plus m1g sine of 37 degrees. And now that I've done that, I can take this expression and plug it in here for the tension. And when I do, I've got this mg sine 53 degrees term, and then I subtract the tension. So minus the first term and also minus the second term. I have to make sure that I distribute that minus sign. And then finally, that equals the mass times acceleration. And I'm being careful of the masses that I use. So I had m1 from the equation for block 1, and I've got m2 from the equation for block 2, and I need to keep those separate. So I've got this down to one equation with one unknown. I don't know acceleration, but I'm in position to solve for that. So let me take this term that has acceleration and I'll add it to both sides. So that on the right, I have m2a plus m1a. And then what that leaves on the left will be this. And on the right, I can factor out the acceleration because it's common to both terms. And then I just divide both sides by m2 plus m1. So on the left, I'm going to factor out, I guess I can factor out a g. That's the only thing that's common. So let me factor out a g and write m2 sine 53 degrees minus m1 sine 37 degrees. And then just like I did on the right, I'm going to divide the left by m2 plus m1. And so this is just my final result for the acceleration. I can plug in some numbers because this is a numerical problem. But before I plug in numbers, I always like to do everything symbolically so that I can check if this makes sense. That's a really important step. And if you actually have taken the practice exam, you'll notice that there's problems involving find a mistake. And one of the best ways to do that is to look at the symbolic expression that you get for your answer and consider what would happen when some of the parameters are certain values where you would know what to expect. So if I go back to this, this diagram, it's not really that obvious what to expect for this particular geometry. But I know if these angles were not 37 and 53 degrees, but if they were 0, I know exactly what to expect. Nothing would happen. The blocks wouldn't roll because they'd just be on a horizontal surface. So let me see, what would happen if 53 degrees went to 0? Well, then this first term would be 0. And if 37 degrees went to 0, this second term would be 0, and I'd get an acceleration of 0, which is what I would expect. The other thing I can consider is what would happen if both angles went to 90 degrees. If both angles went to 90 degrees and the masses were the same, I would expect them just to hang there with an equal mass on both sides of a rope hanging over a pulley. And so let me see what happens there. If these angles go to 90 degrees, then the sine of 90 degrees is 1. And if m2 equals m1, then the numerator would be 0, and I would again have no acceleration. Other things I can check, if both these angles go to 90 degrees and I set one of the masses equal to 0, the other mass would just fall straight down with an acceleration of g. So again, if we can imagine that these sines just went to 1, that represents the system where the angles involved are 90 degrees. So I just have this. And now if I take away one of the masses, let's say I set m1 equal to 0, what I should get is this other mass just in free fall with an acceleration of g. And that's exactly what I see. m2 cancels, and I get an acceleration of g. So this is behaving the way I expect. So I can plug in some numbers here. And if I just use the numbers that are given in the problem and work this out, I've done that ahead of time. I get 2.352 meters per second squared. And the problem involved numbers that only had, the number with the least number of significant digits was the mass of this 10 kilogram cart. That only had one significant digit, so I should call this 2 meters per second squared to 1 sig fig. So we're not done with this problem. We still have to calculate the tension, but we have an expression for the tension right here that we can plug our acceleration into. So I'm going to plug in not 2 meters per second squared, but I'm going to plug in my 2.352, my more complete and unrounded value in for the acceleration here. And when I do, I get a tension that's 82.32 newtons. And again, I can say that that's 80 newtons to 1 sig fig. So at this point, I'll pause. And if you have any questions, feel free to type them into the chat. Okay, so I see there was one question as I was going about why the acceleration was the same for both blocks. Because they're connected by a string, however fast this block on the right goes down, the block on the left has to go up at the same rate. So that string constrains their accelerations to have the same magnitude. And because I've chosen a consistent direction for positive, when the cart on the right goes down, that's positive. The cart on the left goes up, that's positive. That means the accelerations will be the same. If I had chosen a different coordinate system, like positive was up the incline, I would have to use the acceleration of one block might be minus the acceleration from the other block. But it just depends on your definition of what's positive and for each of the blocks. Why did I cancel out M1 sine 53 and sine 37? So why did I cancel out these red values, these values that I crossed out in red? Those are still there. I'm not getting rid of them. What I'm doing is I'm considering what this expression that I calculated would give me, not for the case that I was asked for in the problem, but for a case where I know what to expect. So that's a really powerful thing to do when you have a solution that you aren't sure if it's right or not. So I was changing this problem to change the angles and to change the masses. So if I set M1 equal to 0 kilograms, and I set 53 degrees equal to 90 degrees, what I'm doing is I'm changing this problem to be one where I've got a mass hanging and there's nothing on the other end. And so this just falls down in free fall. So I know what to expect there. I know that the cart should accelerate with an acceleration of g. And so that's what I'm doing when I cross these out. I'm considering what happens when those values have a different value. But when I actually want to calculate a numerical value for this problem, I don't cancel these out. I don't set the angle equal to 90 degrees. Let's see if I can undo what I did. Yeah, I can calculate those angles with the values given. And yes, I will post this. I will post the recording of this later. Actually, don't know if I'm recording. I will post the notes though that I'm writing in, so that you have it later. Let me actually turn on the recording. That's a really good point. I guess the first question won't be recorded, but I've turned on recording now, so that the next several will be. Any other questions about this one? The important parts are drawing careful free body diagrams, using those diagrams in Newton's second law. Once we do that, it's a bunch of math, right? So there's really no physics involved there. But then when we get our answer, interpreting that answer and making sure it makes sense is really important to do those physical checks. Yeah, you may be thinking I'm recording from the iPad. I'm actually not. It's got this little record button lit up, but it's not because I'm recording this. It's because I'm sharing it to Zoom. And the iPad treats those two things as being equivalent. Okay, well, let's take a look at the second problem here. We've got this block that's going to slide down a curved surface. It's 200 grams, and it starts at rest at point A, slides down this curved surface, and at point B is moving at 8 meters per second. Then it slides an additional 10 meters to point C, where it comes to rest. Okay, so there's we're not told how much friction there is on this surface, but there is some friction. And we want to figure out how much work is done by friction between A and B. And then we want to figure out what the coefficient of kinetic friction is that causes it to stop after 10 meters once it reaches the flat part. Okay, so for this problem, we have a block sliding down an incline, which is very similar to what we had in the last problem. We had a block on an incline. And in the past, we were able to use Newton's laws to understand what was going on. Here, that's not going to be so useful. This surface that it's sliding on is curved. And so calculating like the component of the force that points along the surface is tricky because it's going to keep changing as the angle of the surface changes. So that's not a very useful way to do this problem. But because we're asked about work, that should be a hint that we should be thinking about energy, right? Work is a transfer of energy. And so we can actually use conservation of energy here, and we'll treat this as an open system, one where energy is being added or subtracted. In this case, it's being subtracted from the system by friction. And so in general, our conservation of energy equation looks like the initial energy plus any work done by non-conservative forces equals our final energy. That's true anytime you're using conservation of energy. What we need to do is make this specific for this particular problem. So for the first part, question A, I care about the motion from point A to point B. So I'm going to treat A as my initial point. So I'm going to call that energy at A, and I'm going to treat B as my final point. So we'll call that energy B. And the work done as the block is sliding down is due to friction, and that's what I'm trying to solve for. Okay, so I can rewrite this solving for the thing that I care about. The work done by friction is the work done by non-conservative forces. It's going to equal EB minus EA. And now I need to evaluate what the energy is at point B and at point A. So at point B, I know the block is moving at a speed that I'll call VB, and I'm told it's 8 meters per second. I'll also say its height at B is equal to 0 because it's at the bottom. If I do that, I can say the height at A is 4 meters from the diagram. And I also know the velocity at point A is 0 because it's released from rest. So what that tells me is at point B, there is no potential energy, but there's kinetic. So I can write in the energy at point B is 1/2 mv squared. And at point A, there's no kinetic energy because it's not moving, but there is potential energy. It's going to look like mg times the height at point A. And so it's just a matter of plugging in numbers here. I have a 0.2 kilogram mass that was moving at 8 meters per second at point B. And we're going to use 9.8 meters per second squared as our value of g, and 4 meters as the initial height. This will let me calculate a numerical value. I get minus 1.44 joules when I do that. Okay, so the minus sign worked out because this first term was smaller than the second term. And it makes sense because the work done by friction is always negative. It's always taking energy away. So I expect it to be negative. And that's in fact what I see. Okay, well, that was the first part of the problem. I want to do the second part of the problem. What is the coefficient of kinetic friction along the horizontal surface? So for this, I'm going to apply conservation of energy again between points B and C. At point C, the block has just stopped. It's lost all of its energy. So whatever energy it had at point B must have been taken away by friction. And of course, the stronger the frictional, the greater the coefficient of friction, the faster it will take away energy. So let's again write conservation of energy. It's going to look like the energy at point B plus the work done by non-conservative forces is the energy at point C. Okay, now the work done by non-conservative forces, in this case, it's just friction. So it's going to be the friction dotted with the displacement. That's our definition for work. And so this force of friction, I need to work out. So the block sitting on the surface has some weight mg, has some normal force that opposes that. And so in the vertical direction, I can clearly see that n must equal mg. I can find that by adding up the forces and setting them equal to mass times acceleration, which is 0 in the y direction. Okay, well, as the block moves to the right, friction must point to the left. And the force of friction for a sliding object is mu k times n, which is the same as mu k times mg in this case. And because it's pointing to the left, that's going to be in the minus x hat direction. Whereas delta x, the displacement of the block, is 10 meters to the right. And as a result, I'm going to get a negative value for friction, mu k mg. I'm just going to call this delta x for now. I'll plug in 10 meters again later when I solve the rest of this. Okay, so I already know what the energy at point B is because I used it in the previous part of the problem, right? It's right here. So I can just write that again, 1/2 mvb squared. The work done by non-conservative forces, I've just found, it's minus mu k mg delta x. And the energy at point C is 0 because the block comes to rest and it's at the bottom. Question here, why is friction negative? The force of friction is negative because it's pointing to the left, and I define to the right as being positive when I plug in 10-meter displacement. The work of friction is always negative. Friction always dissipates energy and takes it away. So when I multiply these together, I get a negative work, which is what I would expect. If I just want to calculate the magnitude and then say that it's negative, I can do that as well. The final reason for why we could say it's negative is friction points to the left, displacement points to the right, and the dot product of the two is F times delta X times the cosine of the angle between them. And that angle is 180 degrees. And that will give us the minus sign. The energy at point C is equal to 0, because if we go back to the problem, our block slid down and then came to rest at point C. So there's no kinetic energy at point C. And because it's at a height that I've defined to be 0, there's no potential energy at point C. So this is saying whatever energy the block had at point B got dissipated by friction, and now there's none left. Okay, so our equation is set up for that, and we're trying to solve for mu k. So the first thing I can do is just bring the negative term over to the right side. And then I'm going to divide both sides by mg delta x. When I do that, the m's cancel out, and I'll get an expression for mu k that looks like vb squared over 2g delta x. Okay, so I want to evaluate this numerically. I have 8 meters per second as vb, my usual value for g, and 10 meters for delta x. So numerically, this is giving me 0.327. And let me check the units. I've got meters per second squared in the numerator, and I've got meters squared in the denominator and per second squared. So the units are all canceling out. So this is going to be dimensionless. That's what I expect for a coefficient of friction. It should be dimensionless. And if I go back to the problem, I had 3 significant digits that I need to keep. So I've written this with 3 significant digits. Okay, I see there's a couple questions in the chat. Go ahead and type in any more that you might have, and I'll try to address the ones that I already see. So question, can we use kinematics and then solve for frictional force, then solve for mu by dividing by the normal force? Yes, you can. You could solve this problem from B to C. You could find the frictional force. With that frictional force, you could figure out the acceleration. With that acceleration, you could figure out how far it goes before it stops. You could do that system in reverse to figure out the coefficient of kinetic friction. Knowing that it goes 10 meters, you could, for example, say v squared minus v naught squared is 2a delta x. We know delta x, we know v naught, we know v. You could solve for a. From that a, you could say that's force over mass. The force was mu k mg over m. You could solve this for mu k. So yeah, there's more than one way to do this. Does the distance between B and C being 10 meters not affect the number of significant digits? It does affect it. However, in the diagram, it says 10 meters. In the problem, it was 10.0. So I'm using the value in the notes. Can I explain why minus EA equals minus MGY again? So right here, this minus EA, I wrote was minus MGY, sure. So what we're saying is the energy at point A must be MGY at point A. So point A was the point where the block was released from rest. And so if it's released from rest, it doesn't have any kinetic energy at this point. Its velocity was 0, no kinetic energy. It does have potential energy because it's 4 meters above the ground. So that height I'm calling Y sub A. And the potential energy that an object has is just mgy. So mg times y at point A is the energy at point A. So should part A be 2 sig figs because of the height? So the height, yeah, that's an interesting point. I meant to put all the numbers into 3 significant digits in the problem, but I didn't type in the height. So given a height with 2 significant digits, for part A, we should only have 2 significant digits in our answer. Yes, I will agree with that. So interesting question, though. Should our answer for part B have only 2 significant digits? If we look at what we used to calculate it, we didn't use anything about part A. We were told the velocity at part B was 8 meters per second. So given that, we didn't use the value for part A, so we could still have 3 significant digits in part B. Okay, I'll give you a couple seconds to get any further questions in before I go on to the next problem. Okay, it looks like we can move on. Okay, so example 3, I tried to find a problem that would involve some conservation of energy and also involve springs, because we haven't done a lot of spring problems. The homework on conservation of energy didn't involve springs. So before we get started on this problem, we can see that it has a spring in it. And so that's sort of 2 things that I want to note about springs is the potential energy stored in a spring is 1/2 k delta x squared, where delta x is how much the spring is compressed from equilibrium. And the other thing is the force that a spring exerts is minus k delta x. Those are 2 equations that relate to springs that may be useful here. Okay, so we've got this block of mass m sitting at the top of this hill of height h. There's no friction, and it's released from rest. So it's going to slide down the ramp. When it gets to the bottom, it's going to slide and crash into this larger block of mass big M. Now we're told that the 2 blocks stick together. So maybe they've got glue on them, maybe they've got Velcro, we don't know, but for whatever reason they stick together. And then the whole system would move to the right. So both blocks together are going to move to the right, compressing the spring. So they will push the spring in until it's fully compressed and they can't go any further. And at that point, they will temporarily be stopped. The spring will probably push them back and they'll probably get launched up the hill again. But the question stops once the spring is fully compressed. So the question is asking to figure out how far the spring gets compressed. So let me just kind of sketch what that might look like. We've now got the little mass and the big mass stuck together, and the whole thing is compressed by an amount that I'll call delta x. Okay, so this is a conservation of energy problem. If we look at it, we have some object at a certain height, and it's going to come down, and the higher it starts, the faster it'll be moving. And the more energy it has, the further it can compress the spring. However, before it compresses the spring, the small mass is going to collide with the big mass. And energy is not conserved in collisions. In particular, because they stick together, I know this is a completely inelastic collision, which is just another reminder that energy is not going to be conserved. So while I can consider conservation of energy as the block goes down the ramp to figure out how fast it's going at the bottom, I can't use conservation of energy from the very top to the very end. Rather, what I'm going to have to do is I'm going to have to consider the point where the block is moving with some speed v just before the collision. And then just after the collision, I'm going to consider both blocks moving at some common velocity v prime. And I can use conservation of momentum during the collision to relate v to v prime. And then once I do that, I can use conservation of energy as these moving blocks going to the right transfer their energy to the spring. Okay, so that's how I'm going to approach this problem. All right, so step 1. Conservation of energy as the block slides down the ramp. But I'm going to stop just before it collides with the big block. So it's a frictionless ramp. So I have a closed system, and I can just say the initial energy equals the final energy. There's no work being done by non-conservative forces taking away energy as the block slides down the ramp. And so initially, because I'm told the block is stationary when I release it, there's no kinetic energy, and its initial energy is entirely potential. So I have mg times h as my initial energy. Now, once the block is at the bottom, right here, and it's moving at some speed v, it no longer has any potential energy. I've sort of implicitly described the bottom height as being y equals 0. So it's no longer got any potential energy, but now it has kinetic energy. That's where its energy went. So it's now kinetic. Okay, so the masses cancel. I can solve for v. I'll multiply both sides by 2, and then I'll take the square root to get that at the bottom, the block is sliding at square root of 2gh. Hopefully this expression looks familiar to you. Anytime we drop an object and there's no friction or air resistance, after it travels a distance h, it will be moving at a speed of square root of 2gh. So having recognized that, I'm going to assume that this is correct and move on. And I'm going to consider conservation of momentum next. So step 2, we're going to do conservation of momentum from just before to just after the collision. So momentum is conserved in collisions. In fact, that's when using conservation of momentum is particularly useful, because energy is not conserved in collisions. So momentum gives us an alternative way of analyzing what happens in a collision. Whenever there's no external forces on an object or a system of objects, then we can say momentum is conserved. Okay, so initially we have this small mass m moving at some speed v, which I just calculated. And the big mass is not moving, so it has no momentum. After the collision, they move together as one common object. So I treat them as having some total mass, little m plus big M, and moving at some speed that I'm going to call v prime. So now I can work out what v prime is in terms of v by dividing both sides by the total mass. That gives me that v prime is little m over little m plus big M times v. And if I want to plug in my value that I got for v from the first part, I can do that. Okay, now I'm still not done. There's a third part to this problem. Now that the blocks have collided, they're moving to the right, and that kinetic energy that they have is going to get transferred into the potential energy of the spring. So we said the potential energy in a spring is 1/2 k delta x squared. So we're going to use that along with conservation of energy in step 3. So we're going to use conservation of energy from just after the collision until the spring is fully compressed. So again, we have a closed system. There's no work being done by friction or other non-conservative forces changing the energy. So just whatever initial energy I start with is going to be the energy that I end with. But initially, that energy is all kinetic. So I have the blocks moving together, so I consider their total mass, moving at some speed that I was calling v prime, and I have an expression for that I will plug in a moment. So there's the kinetic energy of the blocks when they start to compress the spring. And as the spring compresses, the blocks are going to slow down. And when they finally are no longer moving, then all of the energy is potential energy in the spring, which has the form 1/2 k delta x squared. And it's this delta x that I'm trying to solve for. So the 1/2s cancel, and I can divide both sides by k, and I get an expression for delta x squared. It's little m plus big M over k times v prime squared. And then I can evaluate my value of v prime. So I get little m over little m plus big M times square root of 2gh. And that whole thing gets squared. Okay, so there's a fair amount of simplification I can do. I'll do some of it. So I'm going to go through and square, and then I'm going to cancel out one of these. I'm going to get m squared over k times 2gh. So let me do this. Let me say I found the amount that the spring gets compressed. And let me see if this makes sense. One of the things that I want to check is that my dimensions are consistent. If you're plugging in numbers, then the easiest way to do that is just keep track of the units and make sure they give you the right units. In this case, I wasn't given numbers. I just have these parameters. But I can think about what the units would be. So let me say that m is a mass. It's going to be measured in kilograms. So it's like I have kilograms squared in the numerator. And then I have a g times an h. So g is meters per second squared. And h would be in meters. And in the denominator, I have k. So I have to think about what the units are for k. And I can go up to, let's say, this expression, and I can see that k must be measured in newtons per meter in order to make this expression hold. When I multiply by a distance, I need to be able to get a force. So k would have SI units of newtons per meter. And if I work this out, some of these things can combine and cancel, and other things can't. But I can simplify this by sort of combining the meters in the numerator together. And in the denominator, I'm going to write newtons as a kilogram meter per second squared. And then I've also got per meter. So the meters cancel out there. And let's see what I get. I'm getting the seconds canceling out. And this kilogram canceling one of those. And I forgot to include the mass. The mass is going to be in kilograms. So that cancels. And what I'm left with is meters squared for my displacement. That's a problem, right? Displacement is not measured in meters squared. It's measured in meters. So I made a mistake. So let's see what I did. I solved for delta x squared, not delta x. In order to get delta x, I need to take the square root. Okay, so let me go through. I'll look through the questions that were asked while I was going through this. If you have other questions, feel free to type them into the chat, and I'll try to address all of them. Okay, so one question. What would change if this collision were elastic? Okay, so if we go back to the problem, we're told that the blocks stick together. So when things stick together in a collision, then that's not an elastic collision. If it was an elastic collision, they would bounce off of each other. So that's the first thing. We couldn't have the problem as written with an elastic collision because the blocks would bounce off of each other. So what would change is energy would be conserved. So over here at this point where we applied conservation of momentum, that conservation of momentum would still hold, although these two masses wouldn't be moving at the same speed. They would be moving at different speeds. So I would have one term for each mass instead of one combined term. That would give me an extra thing that I didn't know. Instead of one velocity after the collision, there'd be two. And I would have to write an equation for conservation of energy during the collision to solve for that second unknown. So the math would get more cumbersome. There'd be more equations with more unknowns. But the work that we did would still be valid. We would just have to rewrite it to account for the blocks not sticking together. Can I show the beginning of step 3 again? Sure. So this was the step where we're considering what happens as the blocks moving together compress the spring. So we're applying conservation of energy, and we're saying initially we have these two blocks moving. So there's some kinetic energy. And then The final point that I'm considering is when the spring is fully compressed. So at that point, all the energy is stored in the spring, 1/2 k delta x squared. And yes, we use conservation of energy there. That's what we're using as the spring is compressed. We use conservation of energy because there's no work being done by friction. So it's easy to say that whatever initial energy we have is the final energy. We can't use conservation of momentum in step 3 because momentum is not conserved in step 3. There's an external force from the spring slowing down the blocks, right? They're moving to the right initially, and then they come to rest. So clearly their momentum has changed. But we can use conservation of momentum during the collision. In fact, we pretty much always use conservation of momentum in collisions. We don't use conservation of energy because when things collide, there's usually some energy that's mechanical energy that's lost as the objects heat up or deform or otherwise dissipate energy. What happened to the other m plus big M? So I think you're referring to, I had an m plus big M squared here. I had an m plus big M on the top, so I canceled off one of those factors. In step 2, why was the initial velocity of m equal to 0? The initial velocity of little m was not. Okay, so let me go back to step 2. Step 2 is the collision. So before the collision, my little mass was moving to the right at speed v, as drawn in blue here. My big mass was just sitting at rest, waiting to be collided with. So the little object had some momentum, the big object did not. And that's why I wrote some momentum mv for the little object, but the big object had no momentum because its velocity was 0. Oh, why isn't there did I miss a little m plus big M in my final answer? Yes, I did. I missed that. Thank you. So my final answer here should have a little m plus a big M in it. Thank you. So I'll give you about 10 more seconds to get in any further questions on this problem before we move on. This is one of those problems that involves conservation laws, but we have to know when to apply them. That's really the key. So when things are moving up and down, oftentimes that's a good time to use conservation of energy because we can convert the change in potential energy to a change in kinetic energy. When things collide, we can't use conservation of energy. But we can use it before the collision and we can use it after the collision. So you did that in the homework, I think it was homework 8, where you did that, and we did that here as well. So breaking up the problem into different intervals when different things are conserved can be helpful in working through the problem. Okay, and we've got one final problem. This one involves quite a few things. Like the last problem, this one's going to involve conservation of momentum and conservation of energy. So I picked it because it includes quite a few different things that we care about. So this is kind of maybe a little bit contrived problem, but imagine we've got this big ramp here that's on wheels such that it can roll freely left and right. And on the ramp, we put another object, a little cart, that also has wheels, so it can roll freely. And we release that cart from rest, initially at a height h. So what we expect is the cart will roll down and go off the end of the ramp to the left. But as this cart is rolling down and getting accelerated to the left, the big ramp is going to feel some kickback or some recoil, and it's going to move to the right. And so we get the cart going this way and the ramp scooting out from underneath it. So after the cart has gone down, we expect the ramp to be moving to the right and the cart moving to the left. All right, so we want to figure out how fast the cart and the ramp are moving after this happens. Okay, so the first thing that when we look at this, one object, initially the objects are both at rest, they're just sitting there, and then the cart moves to the left, the ramp moves to the right. We should be thinking conservation of momentum here. We have one object moving left, one object moving right. When we have multiple objects interacting like this, it's often useful to use conservation of momentum. So let's say momentum is conserved. And initially, the momentum is 0 because my block is at rest. So there's nothing going on. So at the bottom, once the cart is moving to the left, the momentum of the cart is going to be minus mv cart in the x direction. So if v sub c is the speed of the cart, the fact that it's moving to the left gives me a negative velocity and therefore a negative momentum. But the ramp also has some momentum, and it's going to be moving to the right, so its momentum is positive. And I'm going to use a capital M, and I might even put a subscript R and a subscript C on the masses. Otherwise, my capital M's and my lowercase m's might start to become indistinguishable. So it's going to be moving to the right with some velocity for the ramp that I'll call v sub r. And so conservation momentum tells me the initial momentum must equal the final momentum, which is the sum of these two. Okay, so I'm going to say initial momentum equals the final momentum. And that initial momentum is 0. So I get a relationship between the mass of the cart, the velocity of the cart, mass of the ramp, and velocity of the ramp. So I could, for example, solve for the velocity of the cart. It's going to be mass of the ramp over the mass of the cart times the velocity of the ramp. Okay, now this on its own isn't that useful because I don't know v sub r. I don't know how fast the ramp is going to be moving. So this doesn't tell me how fast the cart is moving. It only gives me a constraint. In order to solve this equation for VC and get rid of this VR, I need another equation. And so my other equation here is actually going to be conservation of energy. So in the previous problem, we said that during the collision, energy wasn't conserved, but momentum was. Here, as this cart slides down, we're saying momentum is conserved, but we can also say energy is conserved. There's no friction involved. There's no work being done to add or subtract energy from the system. So I should be able to say the initial energy, which is all potential, equals the final energy, which is all kinetic. So the kinetic energy of the cart is 1/2 times the mass of the cart, velocity of the cart squared. And the kinetic energy of the ramp is going to be 1/2 times the mass of the... Okay, I can't write that far to the right, or else I hit the scroll bar. 1/2 mvr squared. So let me apply conservation of energy as the block is sliding down the ramp. And so here I have mgh being the initial energy, and then 1/2, this is the mass of the cart, times its velocity squared. That's the kinetic energy the cart has when it shoots off at the bottom. And the kinetic energy that the ramp has is 1/2 times the mass of the ramp times the velocity of the ramp squared. And notice that we don't care about the direction that these objects are moving, because as long as they're moving, their kinetic energy is positive. So these things add up. That's very different than when we added up their momentum and they were moving in different directions, so they canceled out. Okay, so anyhow, I've now got two equations, this one in green and this one in red, and I've got two unknowns. I don't know VC and VR, but I can take this value for VC and plug it into this expression and then solve for VR. So let me do that. Oops. So I'm already losing track of the fact that my ramp I was going to write with an uppercase M. So I'm glad I kept those subscripts on there. Okay, so now I've gotten rid of the VC and I can just solve for VR, which will be my next step. So on the right, both terms have a VR squared in it. So I'm going to factor out the VR squared. I get something times VR squared. And that something, I'm going to now factor through, do my squaring and canceling. So I'm going to have an MR squared in the numerator and one factor of MC in the denominator, because this MC gets squared, and see, this MC gets squared, and this one removes that factor of one factor. The rightmost term has a 1/2 MR in it. And so let me multiply both sides by 2. When I do that, then that 1/2 goes away. And now, let's see, what's the easiest way to proceed? Let me divide both sides by MC. And when I do all that, I get 2GH on the left, and on the right, I get MR over MC quantity squared plus MR over MC not squared times VR squared. So I'm trying to solve for VR, the velocity of the ramp here. So let me just divide both sides by this factor that's in brackets, and then take the square root, and that will give me my answer. It's going to look like square root of 2GH over this parameter in brackets, MR over MC squared plus MR over MC. So that's the velocity of the ramp. I now plug that back in to my expression I got from conservation of momentum to get an expression for the velocity of the cart. It's going to be the mass of the ramp over the mass of the cart times this. Okay, so I'm not going to write the entire thing out on each step. I'll just keep this term in brackets unevaluated for the moment. And now, to simplify this, let me bring this term that's in parentheses out front inside the square root by squaring it. Now when I write out the term that's in brackets, we'll see that I get some cancellation. So I'm going to cancel this and that by dividing the top and the bottom by MR squared over MC squared. And my denominator becomes 1 plus MC over MR. My numerator is just 2GH, and the whole thing is square root. Okay, so I have an expression now for the velocity of the cart and an expression for the velocity of the ramp. And I just want to do a little error checking, make sure these make sense. So the first thing I can do is check the dimensions. Square root of 2GH is a speed, right? G is meters per second squared, height is meters, so this is meters squared per second squared, and square root of that is meters per second. The denominator is dimensionless because I have 1 plus a ratio of masses. So the units are correct. And the next thing I want to consider is some case where I know what to expect. So for example, going back to this problem, if this ramp were really, really heavy, so it's made of granite or something like that, and this cart is really light, I would expect the ramp not to move much at all. So let's see what happens when we let the mass of the ramp get really large. When the mass of the ramp gets really large, the denominator in this expression for the velocity of the ramp gets really large, meaning the velocity of the ramp goes to 0, which is what I expect. And then likewise, the velocity of the cart ends up being square root of 2GH when the mass of the ramp gets very large or the mass of the cart gets very small. Either one of those things makes this term go to 0. And then I get a velocity of the cart of square root of 2GH. And if you recall, a couple slides ago, I said that when something falls a distance h, we expect it to be moving at square root of 2GH. I had that in this problem. And so that's what I expect in this problem as well. So that little bit of error checking convinces me that I've solved this correctly. Okay, at this point, feel free to type in any questions, and I'll go through and look over the questions that were asked while I was doing this. Shouldn't it be 1 plus MR over MC in the denominator? No. So in the denominator, what I did here when I canceled this out, I divided the top and the bottom by MR squared over MC squared. So I had, in the denominator down here, I had MR over MC, and I was dividing by MR over MC squared, which is like multiplying by MC over MR squared. And so the MC canceled one of those, the MR canceled one of those, and I end up with MC over MR. And the reason that I know that it shouldn't be the other way around is because I expect that as the mass of the ramp gets really big, that the velocity of the cart should go to square root of 2gh. And so I see that with it the way that I've written it. But if I invert this, if I'd put MR in the numerator of this fraction that's in the denominator, then as the ramp gets really big, the cart is going to be moving really slowly. And as the mass of the ramp becomes really large, the velocity of the cart goes to 0, which is not what I would expect. If I've got a really massive ramp here, I don't expect that I drop a cart and it slides down and then it's not moving at the bottom. That doesn't make any sense. Okay, so you can, if you're not sure about one of the math steps, you can always rely on your error checking to see if what you end up with makes sense. Okay, so I don't see any other questions, and that's sort of all the time for new content we have. But we have about 8 more minutes, so if you'd like to stay in the call and ask any questions, you're welcome to do that. If you want to drop off now, you're welcome to do that as well. Are these lecture? Yeah, I will post these on Canvas. Yes. So shortly after 1:15.